All right, so let's get started with our next chapter, which will be chapter 2. In this chapter, we're going to dig a little bit deeper into atoms and elements, which is a conversation we started somewhat in the last chapter, but let's get a little bit deeper into it with this one. Okay, so the first little bit of topic here, so just as some food for thought, and it'll kind of show you where we're going. So in this chapter, I'm going to show you kind of some of the knowledge we have now, and then show you how we got there. Okay, so this story is about two scientists working with IBM. Okay, and they were experimenting with electrical current, which is passed over a flat metal surface. And I'll show you a diagram of this instrument in just a moment. But what they discovered was the tunneling current allowed them to scan the surface at an atomic scale. And they actually ended up winning the Nobel Prize in Physics for this. And I'll show you kind of what it was that they did. Okay, so this is what they were able to do. Okay, so essentially, they were able to take pictures of the atoms. Okay, so what this does is there's sort of a needle that they can drag along the surface, and that needle contains an electrical current. And with that electrical current, they're able to maintain the same distance between the surface of the metal, okay, and the needle at all times. And it will move up and down to maintain that current. So what they're able to see with this is they're actually able to see where the metal surface is higher and where it's lower. And with that, they're basically able to actually read, or you could so to speak, or take a picture of the surface of the metal. So they're actually able to image the atoms. Okay, so you can see in this picture here, you have the little rings. So this is one way that carbon exists in nature. So in things in like a graphite sheet, something like that, or in graphene, you'll see these type of carbon structures where you have six-membered rings. Okay, so they're actually able to get a photo of that. And this technology has come even further to where we're actually able to see things like double bonds between two atoms. Okay, and one cool thing they were able to do with it as well is they were able to do something like this, where they're actually able to write and read the kanji for the word atom, as far as I understand. Okay, so that's just sort of some of the evidence we have for atoms now. So if you remember, when we were discussing laws and theories, I said that the atom was still just a theory. Okay, so we still have some highly compelling evidence that tells us that theory is most likely true. But just remember, it's still a theory. Okay, so we're still evolving and learning about this topic, even though it's something so well established and we've based so much on it. Okay, so just keep that in mind. Okay, so this is sort of an image of what this microscope looks like. Okay, so you can see the electrical current, and you can see that there's sort of a lip here. So as it passes over that, it's going to want to keep this the exact same distance. Okay, it's going to do that by raising and lowering the tip of the instrument. Okay, and with that, they're able to read the surface of the metal, read a metal surface or other things as well. Okay, so I'm not going to expect you to recreate this instrument or really to even understand how it works. That's perfectly okay. All I really want you to understand with this is how compelling of evidence we do have for the atom. Okay, so we're going to start talking about atomic theory now. Okay, so we're going to start from sort of the very beginning of atomic theory, and we're going to progress up to what we know today. Okay, so the first thing, when we talked about this, the law of conservation of matter. Okay, so the law of conservation of matter, this is one of the first principles of chemistry, you could think of it that way. And this tells us that in a chemical reaction, matter is neither created nor destroyed. Okay, so that's a big statement. And what that means is the total mass of the reactants used in a reaction must be equal to the total mass of the products produced. Okay, so if we take a look at this, we're taking sodium metal and chlorine gas to produce sodium chloride. Okay, so regular table salt. And what's important about this is that we're adding 7.7 grams of sodium, 11.9 grams of chlorine. Okay, we have a total mass of 19.6 grams. So that's how much stuff we're putting in. Okay, that's how much matter is going in. And so what's important here is that the amount of matter we get out is also 19.6 grams. Okay, so the same amount that we put in, we have to get out. In other words, the mass of the reactants must be equal to the mass of the products. Okay, so I could, for instance, give you two numbers. I could give you 7.7 grams of sodium and then 19.6 grams of sodium chloride, and you could solve for how much chlorine gas I used, just based on the fact that you know nothing can be created nor destroyed. Okay, so just keep that in mind when you're doing these reactions, or when we start to get into looking at chemical reactions, that everything you put in has to come out in one form or the other. So if you put in carbon, you have to get out carbon. If you put in chlorine, you have to get chlorine back out. Okay, so you're not going to create chlorine through the process of the reaction, and you're not going to create sodium, for instance, through the process of the reaction. You have to get in, or you have to get out what you put in, and you have to put in what you expect to get out. Okay, so the total number of reactant atoms must be equal to the total number of product atoms. So just what I'm saying, if I put 2 chlorines in, I have to get 2 chlorines out. Okay, and I can't just make stuff up along the way. Okay, so starting sort of from the early stages of atomic theory. So there were some more ancient type philosophers that first speculated about a very tiny building block that making up all matter. But we're going to start from Dalton, because even though they postulated very early on that there must be some small indestructible particle, really Dalton is where all of this really starts to come together. Okay, and Dalton said a few things. So the first thing he said, that each element is composed of extremely small particles called atoms. Okay, so he just said we have all these elements, and all the elements are made of atoms, and the atom is just a very small particle. Okay, and here we're going to represent oxygen as these red balls, and then nitrogen as the blue spheres. Okay, so as we carry on, nitrogen is always going to be red, or oxygen will always be red, nitrogen will always be blue. Okay, so the first thing he said is just there are atoms. Okay, so he just said there are atoms, and that all of the elements are made up of atoms. Okay, the second thing he says is that all atoms of a given element are identical, but the atoms of one element are different from the atoms of another element. Okay, in other words, if I look at any oxygen atom, they're all similar. Okay, there's no difference between them. But if I compare an oxygen atom to a nitrogen atom, they're going to be completely different. But there again, all of the nitrogen atoms will be exactly the same. And the third thing Dalton tells us is that atoms of one element cannot be changed into atoms of a different element by chemical reactions. Atoms are neither created nor destroyed in chemical reactions. Okay, so going back to our conservation of mass. Okay, so basically what he's saying is that alchemy doesn't exist here. Okay, so I can't turn an oxygen atom into a nitrogen atom through a chemical reaction. That just doesn't work. Okay, and then I'm neither going to create or destroy any material during a chemical reaction. So if I put oxygen in, I have to get oxygen out. And I can't get nitrogen out if I don't put nitrogen in. Okay, the fourth thing he said is that compounds are formed when atoms of more than one element combine, and a given compound always has the same relative number and kind of atoms. So what he's saying is that if I combine things like nitrogen and oxide, I'll get nitrogen monoxide. Okay, so NO. And what he's saying here is if I combine instead nitrogen and oxygen and I get NO2, okay, that's a different compound than is NO. Or if I combine carbon and oxygen, I get CO, carbon monoxide, versus CO2, carbon dioxide. Those are two different molecules. Okay, so we come up with this idea of the law of definite proportions. Okay, and we'll come to that in just a moment. Okay, so Dalton's atomic theory notes that atoms of different elements can combine to form molecules in simple whole number combination of atoms. Okay, and this brings us to the law of definite proportions. Okay, and what this tells us is that for a given compound, the elements always combine in the same proportion. And then we have the law of multiple proportions. Okay, so two elements A and X can form different compounds by combining in different proportions. So what is this telling us? Okay, so it's telling us that if we're looking at a given compound, say water, H2O, we'll talk about water a lot in this class. So what it's saying is that for any given sample of water, you're always going to have the formula H2O. So the proportions will always be 2 to 1. What the law of multiple proportions is saying is that if instead I have something like H2O2, hydrogen peroxide, okay, well that's different than water. Well, of course it is though, right? So if I have H2O, I have one compound, and if I have H2O2, it's a different compound. Just like in my previous example, if I have CO, that's one compound, but if I have CO2, that's a completely different compound. And I think inherently you know this, but it's good to put this in sort of formal language, right? So of course it's a different compound, but that's what we're talking about. So if they come together to form water, it's always going to be 2 to 1. If it comes together to form something like carbon monoxide, it's always going to be 1 to 1. And those are different compounds than if we combine them 2 to 1, 2 to 2, 3 to 1, whatever it is. Okay, so for any given compound, it's always going to have the same proportions. And if it doesn't, then they're a different compound. And that's it. That's all he's saying. So law of definite proportions, law of multiple proportions. Okay, so we started from just the idea here that atoms exist. Okay, so this particle is called atoms. That's it. Okay, then we said all parts of an element are identical. So if I have any atom of any given element, oxygen, nitrogen, carbon, whatever it is, those are all going to be the same. Okay, so this word identical. Okay, and then we said that we can't change atoms into another atom through a chemical reaction. Okay, so I'm not going to turn oxygen into nitrogen. Okay, and I can't just create or destroy matter. Okay, that's important. Okay, then lastly, he said that when elements combine, they can form molecules. And he said that if they come together to form a compound, they always come together the same way. And then he said if they don't, then they're a different compound. Okay, so that's your Dalton's laws, or Dalton's atomic theory, you may hear it referred to. Okay, so let's dig into law of definite proportions a little bit deeper. Okay, so for a given compound, the elements always combine in the same proportion. Okay, so for example, if I have sodium, I have chloride to make sodium chloride, it's always going to be 1 sodium and 1 chlorine. That's it. 1 to 1 ratio. 1 sodium atom and 1 chlorine atom. If I have something else, NaCl2, which is not a possible compound, but if it was a possible compound, that would be something different. Or if I N2Cl2, maybe that exists. Probably not. Okay? But that's going to be a different compound than NaCl. And what this brings us to is this mathematical relationship. Okay, so if we have a 100-gram sample of sodium chloride, it tells us that I have 39.3 grams of sodium and 60.7 grams of chlorine. Okay, and if I take the two masses, I can make what we call a mass ratio. So I'll just take the mass of chlorine over the mass of sodium, and it gives me this proportion. So this is basically saying this is saying 1.54 in proportion to 1. Okay, so there's 1.54 chlorine for every 1 sodium. Okay, and that's going to exist no matter what. So this is saying I have a 100-gram sample, contains 39.3 grams of sodium, 60.7 grams of chlorine. Okay, so what if I have a different sample? What if instead I have a 58.44 gram sample? Okay, sorry, there's an extra decimal point in there. So if I have a different mass of the sample of sodium chloride, so maybe I pull one out of one container and this one maybe you pull from your house or something, I don't know. Okay, so it's still going to contain the same proportion of sodium and chlorine. So here they're telling us it contains about 23 grams of sodium and about 35 grams of chlorine. Okay, if I again take that mass ratio, what you'll notice is, again, it's 1.54, and again, this is 1.54 to 1. So notice these two things are exactly the same. Okay, in other words, the proportion hasn't changed just because it's a different sample. Okay, so the law of definite proportion tells us if I have a sample of sodium chloride or any compound, it's going to be the same no matter what. And if it isn't, then that's something different. And we can show that mathematically. Okay, so you could break this down and say, okay, I have this much sodium, this much chlorine, what's my mass ratio? And I can do that for any sample, and it won't change. Okay, that brings us back to law of multiple proportions. Okay, so if I have two elements, A and X, they can form different compounds by combining in different proportions. In other words, if they combine in different mass ratios, they're a different compound. Okay, so these combinations can be represented as a ratio, just like we did before. Okay, so a molecule of carbon dioxide has a ratio of 1 carbon to 2 atoms of oxygen, 1 to 2. Okay, so, but then if I take a look at something like carbon monoxide, sorry, this should be carbon monoxide, that's wrong. CO is carbon monoxide. Okay, it has a ratio of 1 carbon atom to 1 atom of oxygen. Okay, so and they break this down for us. So here's carbon dioxide, here's carbon monoxide. Okay, so notice in carbon dioxide I have an oxygen here, and a carbon here. Okay, so it's a 1 to 2 ratio. Okay, so massive oxygen that combines with 1 gram of carbon, 2.67 grams. Okay, so it's 2.67 grams to 1 gram of oxygen. Excuse me, to 1 gram of carbon. But if I look at carbon monoxide, so again, this is carbon, this is oxygen. So the mass of oxygen that combines with 1 gram of carbon, 1.33. So the important thing here to notice is that these two numbers are different. So I have a different mass of oxygen combining with carbon to give me a different compound. One's in a 1-to-1 ratio, one's in a 1-to-2 ratio. So what law of multiple proportion tells us is that of course those are different compounds. They're in a different ratio. So of course they are. Okay, so if I have any given sample of the same compound, it'll have the same ratio. And if it has a different ratio, then it's a different compound. Okay, so here we have a little bit of a problem to try out that just asks us to show that these two sets of data basically agree with law of multiple proportions. So they tell us that nitrogen has several forms of compounds with oxygen, including nitrogen dioxide and dinitrogen monoxide. Okay, so nitrogen dioxide contains 2.28 grams of oxygen for every 1 nitrogen, or 1 gram of nitrogen, while dinitrogen monoxide contains 0.570 grams of oxygen to every 1 gram of nitrogen. So how can we show that this agrees with our law of multiple proportions? So the first thing we want to do is we just want to set up a ratio. Okay, so we're going to set this up so that we have the mass of oxygen, so we'll just say the grams of oxygen over the mass of nitrogen. Okay, we can set up two ratios for this. And what we want to look at is we want to say okay, so we want to say, let's just take the first one. So let's say NO2. Okay, so the mass of oxygen, they tell us, is 2.28 grams of oxygen for every 1 gram of nitrogen. And we want to know, is that proportion equal to 0.570 grams of oxygen over 1 gram of nitrogen? So essentially what you end up with is this statement. So is 2.28 grams of oxygen, that's the question you have to ask, is that equal to 0.570 grams of oxygen? Okay, so they made the math nice and easy for us. And of course, no, this is not true. So that's not a true statement. So 2.28 grams is not equal to 0.57 grams. Okay, so of course this is not a true statement. So what does that tell us? That tells us that NO2 and N2O are not the same compound. Okay, so of course they're not the same compound. And if we look at the law of multiple proportions, it tells us that, if we have different compounds, they come together in different ratios. So we've just shown that the ratio of NO2, oxygen to nitrogen, is different from that of N2O. And that's really all you need to say there. Okay, so if they give us numbers, different numbers, we could solve this a little bit differently. But since they just gave us 1 gram, this was really easy to solve. Okay, so just make sure you kind of understand those laws and that you could solve something like that. Okay, so this next section we're going to talk about the discovery of the electron. Okay, so remember, we're building this atom. Okay, so we have these Dalton's laws that sort of set up how the atom can come together. So he just says there are atoms, and this is how they can come together. Well, what about what evidence do we have behind that? Okay, so first thing we're going to look at is discovery of the electron. Okay, we're going to look at two things here. Okay, so the first one we're going to look at is Thomson's charge to mass experiment. Okay, and he used cathode rays. And he found a few things from this. Okay, so Thomson believed that these particles were the ultimate building blocks of matter. And he used a cathode ray, which eventually became known as electron beam, or electrons. Okay, so we're going to take a closer look at that. And then we're also going to take a look at the Millikan oil drop experiment. Okay, so the Millikan oil drop experiment showed that the particle had the same amount of charge as the hydrogen ion, and that's what Thomson observed. And we'll look at kind of more what that means. Okay, so Thomson was an English scientist, and Millikan was in the US. So the first one we're going to look at is just the discovery of the atom's electron. Okay, so this is the cathode ray experiment. Okay, so this is the Thomson experiment. Okay, so Thomson's charge to mass experiment investigated the effect on a cathode ray when placing it in an electric field. Okay, so the basics of this experiment is we have some detector on the end of this tube. Okay, so we're able to essentially visualize where this cathode ray is impacting. It's somewhat the way a television works, or at least the way they used to. Okay, and so he has a cathode ray firing from this end, so it's firing in this direction. Okay, and what he's going to do is he also has these two charge plates. So there's a charge plate here and a charge plate here. And he's able to turn those on. Okay, and he's able to reverse the poles. He's able to change the voltage, all that good stuff. And basically what we have is we have a magnet. Okay, and then we have some electrical poles. Okay, so we're going to fire the cathode ray through this setup, and we're going to use the fact that we know the charge on these two plates, and we're going to observe where does the beam actually hit. Is it deflected whatsoever? Okay, so is there an electrical component to atoms at all? Okay, so is there an electrical component to the cathode ray? And what he found was that yes, there was some deflection when he turned on the electrical plates. Okay, so with the plates are off, you can see this. Okay, so just a completely undeflected beam, so you'd see a white spot here. Okay, then when he applied the electrical field, what you see is deflected beams. So depending on which way you put the poles, will depend on which way you get deflection. Okay, so a combination of the electrical field and the magnetic field causes the beam to deflect. Okay, so what he found was that charged matter is attracted to an electrical field. Okay, and the light's path is not deflected by an electric field. So if we were to do the same experiment with instead light, you wouldn't see anything. You would just see a dot, or you would just see a spot. Okay, so, but matter itself is attracted to an electrical field. Okay, so what we learned is that, so we say that the cathode rays are made of tiny particles, and what we learned is that they always deflect toward the positive plate. Okay, so that leads us to say that electrons have a negative charge. Okay, what he also learned from this, that the amount of deflection was related to the charge to mass ratio of the particles, and you end up coming with the charge to mass ratio of the particles as minus, so minus because they're electrons, minus 1.76 times 10 to the 8th coulombs per gram. Okay, so that's the mass to charge ratio of the electrons. Okay, so this was Thomson's experiment. So we learned two things here. We learned that, okay, so electrons are negative. At least we'll come to find that later. Okay, we'll learn the charge to mass ratio of the particles. This is an image of the actual instrument itself, or well, a slight variation on the instrument. But what's cool about this is you can actually see the cathode ray bending to the electrical field. Okay, so I thought that was pretty cool. So this is an actual image of this. And if you just look up Thomson's experiments or Thomson cathode ray experiment, you'll be able to find these images. Okay, or Thomson's charge to mass ratio experiments. Okay, but I think it's pretty cool because you could actually see the beam bending. Okay, so this is the actual electron beam itself. The next experiment we'll talk about is the Millikan oil drop experiment. So this experiment goes hand in hand with Thomson's experiment. And this experiment helped us to understand a little bit more about the electron. Okay, and I'm just going to describe the basics of the experiment, and then we'll talk about what we actually found from this. Okay, so essentially we have oil inside of an atomizer. So essentially like a perfume mister, something like that. Okay, so we're going to spray the oil into this chamber. Okay, it's going to become so finely misted that it'll actually turn into individual atoms. So what we have is a small hole inside of a plate. Okay, so this plate will be positively charged, and there's a hole here. Okay, so the particles, so these are basically atomized oil, going to travel from the mister down through the hole. Okay, and essentially what we have is a positively charged plate. Okay, we have a negatively charged plate. And we can control through variable switches or what have you. We can control the current and the voltage on these plates. Okay, and on top of that, or surrounding this, so we also have an ionizing radiation ray, and we have a light source. Okay, then in addition to that, we have a viewing microscope. So you can imagine you can see right into the chamber, and you can actually see individual particles as they fall. Okay, so the purpose of the ionizing radiation is to actually turn these into ions. Why into ions? Well, that way we can actually manipulate them with the charged plates. So essentially what they were able to do is to control the voltage on these two plates so they could actually suspend, so they could move the atoms up or down, so the charged particles up or down, and they could actually suspend them within the two plates. Okay, and then they could observe them. And from that, they could read, okay, well, what charge did I have to use in order to make the particles or the ions stop moving? What charge did I have to use to make them go in reverse? And you can kind of get the idea here. Okay, so from this experiment, we were able to determine the charge of the electron. Okay, so from this experiment, we determined the charge of the electron to be minus 1.60 times 10 to the minus 19 coulombs. Okay, and remember that it's negative because we've established that electrons are negatively charged. Okay, so from this, we're able to actually determine not only the charge of the electron, but also the mass. Okay, so if we put everything we've just learned together, now we have this information. So we have electrons are particles found in all atoms. We now know they're negatively charged. So we say that the electron has a charge of minus 1.60 times 10 to the minus 19 coulombs. Again, it's negatively charged. Okay, and we can also say the electron has a mass of 9.1 times 10 to the minus 28 grams. Okay, so from those two experiments, we're already able to gain all of this information. Okay, so let's think about this. So we've come from just saying, okay, there are atoms. Okay, then we said atoms come together to make molecules, and if they come together in certain ratios, then we have certain molecules. And if they come together in different ratios, we have different molecules. Okay, well then we said, well, matter is made up of atoms, but what are atoms made up of? And that led to the discovery of the electron based on the deflection of an electron beam. Okay, and then from that we determined, okay, the electron is negative. And from there we can determine the mass to charge ratio. And then through the oil drop experiments, we determined what the charge and the mass were based on the mass to charge ratio. Okay, so those experiments gave us all of that. So they gave us some information about the structure of the atom. Okay, but what if I wanted to know more? How can we determine more? Okay, so that leads us to the J.J. Thomson plum pudding model. Or Thomas, excuse me. Okay, so J.J. Thomas, so this is commonly referred to as the plum pudding model. So he said that the atom is composed of a positive cloud with electrons are scattered out throughout it. So this is called the plum pudding model because you can kind of imagine that the red part is sort of like the pudding part with sort of raisins or plums embedded inside of it. So maybe more modernly this would be better called the chocolate chip cookie model, something like that. Okay, but it's just that we have some mass of positive matter with electrons scattered throughout it. What we're going to look at is how do we decide whether this was the correct version of the atom or whether it wasn't. Okay, so he's got everything. So he's got positive material, he's got negative material, so that seems to make sense. Okay, so we know electrons exist now, but is this model of the atom correct? Okay, so this would explain the positive and negative behavior of charged matter. So remember, during the oil drop experiment, if we ionize the atoms, or the particles, we get charged behavior. So of course, so there's some negative part and there's some positive part. So far so good. But does this hold up? Okay, and how can we determine that? Well, this is done through Rutherford's gold foil experiment. Okay, so what Rutherford's gold foil experiment is that we have some source of a particle beam. Okay, so a source of a particle beam, and we're firing it at a thin piece of gold foil. Okay, so we're going to look at how the beam is deflected based on its interaction with the gold foil. Okay, so if it was to, for instance, pass straight through the gold foil with no deflection, what would that tell us? Well, that would suggest that the atom is mostly made up of empty space. Okay, so there's no really dense part of the atom. Okay, so there's nothing to deflect the beam. Okay, conversely, if we fire the beam and it becomes deflected, like this, then what does that tell us? Well, it tells us that there's something in there that's dense enough to actually deflect the beam. Okay, and so let's look at what we actually found. This is a photo of this device, so you can imagine beam being fired and some detectors as well. Okay, so let's look at the results of this. So if the plum pudding model was correct, you might expect something like this. So just undeflected beams. So it's just going to pass through with absolutely no interference, so that would look like this. Okay, so they're just going to pass through with no interference. Okay, but on the other hand, if there is something, so if we have maybe a dense piece of the atom, we're going to see some deflections. Okay, so see deflections. Okay, so which one is it? What did he see? Okay, so this would be correct if we were going to observe the Thomson model. Okay, so we have no deflection of the beam, so it's just going to pass easily between the spaces of the atom. There's really nothing dense enough in there to deflect the beam. So what we actually observed, so if the plum pudding model was correct, this was what we would expect. What was actually observed was that deflection. So we did see deflection of the beam. Okay, and in all directions. Okay, so you actually have a circular detector when you do this. Okay, so you have a circular detector. Okay. So what does that tell us? That tells us that within the atom, there must be something for the electrons or the beam to come in and bounce off of. Okay, so something for it to deflect off of. So it can't pass just directly through. It has to bounce off of something. Okay, so this is what we actually observed. So this tells us that no, the plum pudding model is not correct. So there must be something in there that's deflecting the beam. So what did Rutherford say? Okay, so from the gold foil experiment, the following conclusions were proposed. So the atom contains a tiny dense center called the nucleus. And the nucleus has essentially the entire mass of the atom. Okay, he said the electrons weigh so little, they give practically no mass to the atom. He said that the nucleus was the positively charged portion of the atom. Okay, and that amount of positively charged material has to balance out the negatively charged electrons. And he suggested that the electrons were dispersed in the empty space of the atom surrounding the nucleus. So sort of going back here, so we have some dense material in the center, and then some lighter material surrounding it. Okay, which will lead to, of course, deflections of the beam, and that's exactly what he saw. Okay, so let's look at Rutherford model. Okay, so we said that the atom is mostly empty space with a dense center of mass, and he called this the nucleus, with electrons circling around it. He proposed that the nucleus had a particle that had the same amount of charge and electron, but the opposite sign. So equal charge, but positive instead of negative. So he called these particles or protons, and he just gave them the same charge, but with opposite, or the same charge but with an opposite sign. And he suggested their mass was 1.67262 times 10 to the minus 24 grams. So very, very small still. He said since the protons and the electrons have the same amount of charge, for the atom to be neutral, there must be an equal number of protons and electrons. So if I have an atom of helium, for instance, or of hydrogen, for instance, I have 1 proton and 1 electron, and I have to have that. If I don't, then I have an ion, and that's okay too. Okay, I would just have an ion in that case. But if I have just a regular atom, it has the same number of protons and electrons. Okay, and so what that leads us to next is this idea of the number of protons. So remember that we have this dense center core of the atom containing all of the protons, and we also know now that there's neutrons there as well. Okay, and then we have the electrons surrounding it. Okay, so in all actuality, the number of protons, which again is in the nucleus, determines the element's identity. So not the number of electrons, and we'll see why as we continue. Okay, but the number of protons in the nucleus of the atom is called its atomic number. Okay, so the number you see on the periodic table, 1, 2, 3, 4, 5, those are the atomic number. What that actually tells you is the number of protons. Okay, so each element has a unique chemical name and symbol, of course. Okay, and the symbol is either 1 or 2 letters. So for oxygen, we have just O, and for iron, we have Fe. Okay, and the elements on the periodic table are arranged in order of their atomic numbers. Okay, so in other words, as the number of proton goes up, so does the atomic number, and that's how we've arranged them. Okay, so here they're showing us the difference between helium and carbon. Okay, so helium you see has 2 protons, making it helium, and then carbon has 6 protons, making it carbon rather than helium. Okay, so all I'm saying is that the number of protons determine the atomic number, which also determines the identity of the element. Okay, and what this leads us to is isotopes. Okay, so this next little chunk, we're going to talk about isotopes. Okay, so isotopes are elements whose atoms differ in mass due to a varying number of neutrons. Okay, so remember, ions vary in the amount of electrons, but if we're talking about changing the number of neutrons, now we're talking about isotopes. So what's not going to change? What didn't I say would change? Okay, the number of protons. Okay, so just keep that in mind as we continue. The number of protons doesn't change. Okay, they're the same element because they have the same number of protons. Okay, so same number of protons, in other words, same atomic number, and they're chemically identical. Okay, so it's not a different element. It's still the same element. We have the same number of protons, therefore we have the same element. Okay, we identify isotopes based on their mass number. And the mass number we find from the number of protons plus the number of neutrons. Okay, so if we take a look at, this is just the chemical symbol for aluminum, so that's just like you would find it from the periodic table. We have an atomic number of 13, so that tells us we have 13 protons. But notice that the atomic weight isn't 13. Okay, so we have something else in there as well, right? Well, we have neutrons. Oh, of course, we have electrons too, but remember they're very, very tiny. But we have neutrons in there. Okay, so if we want to know something's mass number, we're going to add up its protons and its number of neutrons, and that will tell us the mass number. Okay, so we're going to talk about what symbology we use for isotopes. Okay, so maybe you've seen or heard of carbon-12. You've probably most likely heard of carbon-12 dating. Okay, so a way that we can determine how old something is. Okay, and you've seen a symbol like this probably before. So you have carbon, and you have 12 up top and a 6 down below. So what do those numbers tell us? Okay, well the first thing you want to know is that, of course, this is the chemical symbol, okay, C for carbon. The second thing we need to look at is that this lower number. The lower number is the atomic number. In other words, it tells us how many protons does this element have. Okay, if it has 6 protons, then it must be a sample of carbon. If it has 7, it's something else. Okay, so if it's 7, it's nitrogen, whatever it is. Okay, and then we have the top number. The top number, remember, is our mass number. So notice it's 12. Okay, so in this one on the left, we have 6 protons, and then we have a mass number of 12. And remember that the mass number tells us the number of protons plus the number of neutrons. So in this particular case, I could easily calculate that I have 6 neutrons as well as 6 protons. What if I take a look to the one on the left? So again, it's still carbon, but notice my mass number is different. Okay, so what's changed? Well, what hasn't changed is my number of protons. And that should be obvious because the protons don't change, otherwise it would be a different element. But also, if you look at your atomic number, that hasn't changed either. Okay, so the only thing that's happened here is that carbon-13 has gained 1 neutron. Okay, so its mass number will be 13 rather than 12. So I have 6 protons, and now I have 7 neutrons. Okay, so that's really all there is to it. So if you remember this information, that's really all there is to understanding isotopes for right now, in terms of their chemical symbols, and determining number of electrons, protons, neutrons, mass number, and identity. All that information I just told you. Okay? So give this a try real quick. Okay, so it says how many protons, electrons, and neutrons are in the following atoms. And they give you some chemical symbols here, as well as the mass and atomic number data. One thing I will say before you get started, this tells you the mass number, okay, not the atomic number. It's a little bit different symbology, but we'll talk about that as well. Okay, so give the video a pause, give this one a try, and see if you can come up with those numbers based on what we just talked about.